In this lecture, we're going to talk about transformations of plane strain. So just in a similar way to stress, where we were able to transform stress components to a new set of axes, we can transform strain components to a new set of axes. It makes sense if you think about it. If you remember about Hooke's law, strains can be written as a linear combination of stresses. So if stresses can transform, strains ought to transform. But the interesting thing is, even if we have something besides Hooke's law that relates stresses and strains, strains transform by themselves to a new set of axes by a certain set of equations. We're going to first take a look at something called plane strain, and it's analogous to plane stress in that in plane strain, all the non-zero strain components lie in one plane. So let's write that down. So PLANE, all non-zero strain components lie in one plane. Now it's often taken as the XY plane where this occurs, but it could be any combination, XZ, YZ, whatever. But we'll stick with the notation that our book does, and let's say we're looking at a coordinate system with X and Y. Now what I'm going to draw on this little block, I've drawn similar blocks like this for stress states. I'm going to draw a block like this for a strain state as well. Not very many books draw this way, but stress is something called a tensor. It's a kind of a level up from a vector. Strain is also something called a tensor. So if I can represent stresses on a block, I ought to be able to represent strains on a block too. But the important thing to remember about strains is that strains have to do with deformations, changes in lengths or changes in angles. So here we have our plane strain state. In the XY plane we have epsilon x, epsilon y, and gamma xy that are not zero in general. But the other strain components, epsilon z, gamma xz, gamma yz, will be taken to be zero. Now later on we're going to relax this, just like we talked about generalized plane stress. We're going to look at generalized plane strain too. In generalized plane strain we can have a strain in the z direction, but the shearing strains gamma xz and gamma yz will be zero. So while we're here, let's just go ahead and write that down. Plane strain is common in very thick machine components. It's kind of the reverse of plane stress. Plane stress is very common in thin components, like a thin sheet metal, like aluminum on an aircraft or something like that. Plane strain is common where you have resistance, an inability of the material to deform in the z direction. That causes no strain in the z direction, but we can still have some deformation in the plane identified by x and y. So what we want to do in this particular lecture is we want to start off taking a look at a known set of strain components, epsilon x, epsilon y, gamma xy, and we want to be able to find the strain components off at any angle that we want. And just like we did for stress, I'm going to draw a block off at another angle to the xy axis. I'll call this the x prime and the y prime axis. And we will eventually be able to have some equations that tell us what epsilon x prime, epsilon y prime, and the shearing strain gamma x prime y prime are in terms of the original strains. Not only just those original strains, but the angle that this block is located at with respect to our original axis. So I can put in here and theta. So, like I said, we know that strains have to do with changes in lengths and changes in angles. So the next figures I'm going to draw are going to show a square that's undeformed and then a square that gets deformed when we put some loads on it that cause some different strains. So to start off with, I have this original x and y axis that I'm going to have right here. And I have a new axis, x prime and y prime. And that axis is at an angle theta with respect to the original x and y axis. I have a square drawn in here of side delta s, and it's aligned with this x prime, y prime axis. This is the undeformed geometry. Now I'm going to look at this square in this orientation, and I'm also going to look at a triangle that's formed underneath of this square. So I'm going to draw that in this bottom picture here. This is still the undeformed geometry, but I have the hypotenuse that goes along the x prime axis. That's this dimension right here, just reproducing that line. And then I can line that up with the x and the y axis in this picture, and this will be the angle theta that I have in here. Now this side length is delta s, and I can identify this as delta y, and I can identify this dimension as delta x. Now from this figure I can figure out a relationship between those sides of those angles of that triangle. Delta x is equal to delta s cosine theta, and delta y is equal to delta s sine theta. This is a nice straight right triangle that we have right here, so we can relate those sides just through the trig functions. If you can imagine this square drawn on maybe a sheet of rubber or something that we can stretch out and deform, I'm going to exaggerate what the deformed geometry would look like, and that'll go on these next two pictures right here. Okay, so I take this square, I'm really going to stretch this out. So the x prime direction is maybe off over here. And that square turns into some sort of a diamond shape. I'm not trying to line those up exactly with the x prime axis, but I don't want to be too far off either. Okay, so this is off in the x prime direction, and again the y prime direction is off this way. Now when I stretch a material, I know that the lengths of this side of the block are going to change a little bit. So this was originally the side length delta s, and that was originally in the y direction. Let's talk about strain in general. We know extensional strain is the change in length divided by the initial length. So if I want to solve for the change in length, that is the strain times the initial length. And if I want to find the final length of something, that would be the initial length plus the change in length, or the initial length plus the strain times the original length. I can factor out an L naught in front of this. I have L naught times 1 plus the strain. Well, in that same way, the side of this triangle is going to be its initial length times 1 plus the strain in the original y prime direction. And on this bottom side, the new length is going to be the side length delta s times 1 plus the strain that was initially in the x prime direction. This angle right here that used to be 90 degrees, that opens up and it becomes a new angle. It expands. The change in angle from pi over 2 radians or 90 degrees is the shearing strain. So at this corner, this new angle right here is pi over 2 plus gamma x prime y prime. So these are the new side lengths in terms of the undeformed geometry in the x prime y prime coordinate system. In a similar way, I want to draw a right triangle. It corresponds, it's not a right triangle, I want to draw a triangle underneath of this picture, where this is the long side of the triangle. Like I said, it won't be a right triangle anymore. It'll be like what this triangle would look like when it's deformed. Okay, so maybe it takes a, maybe it looks like this. And let's put some initial points on here so we can identify them. There's point A, B, and C of the initial right triangle. And those points would move then. They'd be a new location. That would be A prime, B prime, and C prime in this picture. This long dimension is what we just talked about, delta S 1 plus epsilon x prime. But these two sides will also have some strains associated with them. Down on the bottom, that's delta x 1 plus epsilon x. There's no prime there. And this dimension right here would be delta y 1 plus epsilon y. And the angle that was originally lined up with the x and the y-axis opens up a little bit. That angle is going to be pi over 2 plus the shearing strain gamma xy. Well, we know if we have a right triangle, we can relate the sides of the triangles with the Pythagorean theorem. When we don't have a right triangle, we have to use something a little bit more sophisticated called the law of cosines. So let's write down what the law of cosines is. I'm sure you've heard of this, but you may not have used it in a while. Basically what it says is the long side of that triangle squared is equal to the two shorter sides squared added together. Okay, so that's the Pythagorean theorem part. But then with an additional term, 2 times the other two sides times the cosine of the angle in between. And in our case, the angle in between is that pi over 2 plus gamma xy. Going to make a little bit of room. What we're going to do is we're going to expand these terms out and put the strain components in them. Alright, so the long side squared is going to be delta S squared 1 plus epsilon x prime, that quantity squared. Two shorter sides in that picture, delta x 1 plus epsilon x, those squared, and delta y squared 1 plus epsilon y, quantity squared, minus 2 times delta x 1 plus epsilon x, delta y 1 plus epsilon y, and then we're going to have cosine, I'll just bring it down, pi over 2 plus gamma xy. Now we can write delta x and delta y in terms of the angle in delta S. So that's what we'll do next. All right, delta x is delta S cosine theta. So we're going to have a delta S squared cosine squared theta 1 plus epsilon x squared. With the next term we'll have delta S squared sine squared theta 1 plus epsilon y quantity squared. Again we get a delta S squared term, but now we have a sine theta and a cosine theta. And then 1 plus epsilon x, 1 plus epsilon y, and then the cosine of the angle in between. Alright, so let's continue on with our algebra just for a little bit. The delta S squared terms are common to all of these, so they can cancel out. Now let's go ahead and expand this term out. We have 1 plus epsilon x prime squared. So this is going to be 1 plus 2 epsilon x prime plus epsilon x prime squared. And a similar term, but this is epsilon x. Here we have a cosine squared term. And then we're going to expand out the 1 plus epsilon y squared term. And that has a sine squared theta in it. And then we have minus 2 sine theta cosine theta we have, expanding this term out, 1 plus epsilon x plus epsilon y plus epsilon x epsilon y. And here we have a cosine of pi over 2 plus the shearing strain gamma xy. We're shifting a trig function by pi over 2 radians or 90 degrees. That gives us the other trig function, and this is the negative of sine gamma xy. Going to continue on with our algebra for just a little bit. And one of the things that we're going to make use of is that we know strains for most engineering materials are pretty small quantities. If I were to square something that's on the order of a microstrain, it pretty much just goes away. So if the strains are much less than 1, anything like this is going to be pretty much 0. Alright, so let's rewrite it. We have 1 plus 2 epsilon x prime. We have 1 plus 2 epsilon x times a cosine squared theta. We have 1 plus 2 epsilon y times a sine squared of theta. And then, let's see, the negative sign here and here make a positive. We're going to have 1 plus epsilon x plus epsilon y times the sine of gamma xy. Now, when I take the sine of a really small number, we're going to get pretty much that very small number back when we do that in radians. So now I'm going to replace the sine gamma xy with gamma xy. We have 2 sine theta cosine theta. If we look, we have a cosine squared and a sine squared theta. That's equal to 1, and that will cancel out with a 1 on this side. I'm also going to divide through by 2 on each of the remaining terms that are left. So on the left-hand side, I have epsilon x prime. On this side, I have epsilon x cosine squared theta plus epsilon y sine squared theta plus, that 2 will go away. I've got gamma xy sine theta cosine theta. I multiply out by the 1. And then again I have these higher order terms, which means they're pretty close to 0. So what I have with the small strain assumption is this equation that I'm going to put a box around. This tells me what the strain is off at any angle theta. If I know the original starting coordinate strains, epsilon x, epsilon y, and gamma xy. Alright, so showing this epsilon x prime on a square off in the new x prime y prime coordinate axis. If I know those original starting strains and know the angle theta, then I can find that new strain. We need to remember what the positive directions are. Positive extensional strains are in tension. They expand the material. So epsilon x and epsilon y are positive when they stretch things out, negative when it's getting shorter. A positive shearing strain, gamma xy, is on the positive x face and points in the positive y direction. Positive angle of rotation theta is from the x-axis to the y-axis. So I have this equation, epsilon x prime is equal to epsilon x cosine squared theta plus epsilon y sine squared theta plus gamma xy sine theta cosine theta. And there's a trig substitution that I'm going to recall here, that 2 sine theta cosine theta is equal to the sine of 2 theta. When I do that for that last term, I will end up with a gamma xy over 2 times the sine of 2 theta. And this looks a lot like an equation that we've seen before for stress. It's not exactly the same, but let me show you the stress transformation equation we got a little while ago. This was the stress off at some angle. You can think of this as sigma x prime or sigma n, and it was sigma x cosine squared theta plus sigma y sine squared theta plus this tau xy sine 2 theta. And so you may notice in here that epsilon x and sigma x have the same kind of term, epsilon y and sigma y have the same kind of term, but on the shearing term, gamma xy over 2 is in the place of tau xy. So there's this slight difference in the equations that we get for engineering shearing strain than we get for shearing stress. So all the things that we've done for stress transformation can be applied to strain transformation. We're going to look at 3D Hooke's law to relate stresses and strains. Then we can apply Mohr's circle for stress or strain transformations, in 3D Mohr's circle of stress or 3D Mohr's circle of strain. Let me write down the complete set of strain transformation equations in a slightly different form. We can replace the cosine squared theta and the sine squared theta in terms of the double angle as well. Alright, so there they are with the double angle instead of the angle theta. I'm writing it down in terms of sine and cosine of 2 theta. We have epsilon x prime is equal to epsilon x plus epsilon y over 2, which is epsilon average for the 2 in-plane normal strains, plus the quantity epsilon x minus epsilon y over 2 cosine 2 theta, plus gamma xy over 2 sine 2 theta. If we put into here theta plus 90 degrees, we will get this equation down here. We have 180 degree shift in the cosine and the sine function, which causes a negative sign on these two terms. Epsilon x plus epsilon y over 2 minus the quantity epsilon x minus epsilon y over 2 cosine 2 theta minus gamma xy over 2 sine 2 theta is equal to epsilon y prime. And we haven't shown it yet, but we will. It'll turn out to be gamma x prime y prime over 2, there's that factor of divide by 2, is equal to minus quantity epsilon x minus epsilon y over 2 sine 2 theta plus gamma xy over 2 cosine 2 theta. When it's convenient, I may refer to this as epsilon n, and I may refer to this one as gamma nt divided by 2. These equations are the plane strain transformation equations. I do not expect you to memorize these equations. And in fact, I will ask that you do not even try to memorize these equations. They're in your book, they're here in the notes. We can get to them if we need them, but we're going to learn how to use more circle of strain instead of memorizing these equations. Now that said, you need to know how to apply these equations in case you need to program them into a spreadsheet or a computer program or something like that. There's a couple things that I want to point out about these equations. Just like we had for stress, if we were to add epsilon x prime and epsilon y prime together, we will get epsilon x plus epsilon y. See how those two terms there will cancel out, and the average strains will add together to make epsilon x plus epsilon y. The other thing I want to note are these are very similar to the stress transformation equations. But with sigma x getting replaced with epsilon x, sigma y getting replaced with epsilon y, and gamma xy, tau xy getting replaced with gamma xy over 2. And this thing is the thing that's a little bit different. We have to be careful about that. And when we do our Mohr circle of strain, we will have to account for that divide by 2 when we set it up. So now I can complete this picture. These equations will allow me to tell the numbers for the strains on this new block at this new orientation for any angle theta that I want, knowing the original strain state. All right, we're going to continue this lecture just a little bit, and we're going to talk about something called strain gauges, and then after we talk about that, we will get the shearing strain gamma x prime y prime. So let's talk about strain gauges and then something called a strain gauge rosette. So a strain gauge is an electrical device that can be used to measure strain. You may have learned in physics that if you stretch out a wire, the resistivity of the wire changes. Okay, so you have a wire. I'm just going to draw this like it's a bar. You can think of this as a very thin, long wire. And as you stretch this out, it changes the length. And as you change the length, because of Poisson's ratio, the cross-section also changes. The resistance, the ohms, change. So we have a change in resistivity as we apply a load to it. The problem with a wire, a single wire, using a single wire as a strain gauge, it's possible, but the change in resistance is really tiny. We're talking about maybe micro ohms. It's a very small change in resistance. To get something that's very measurable, you might have to have something that's longer than your component that you want to test. Well, back in the 1940s or so, people came up with a very clever way to take advantage of this change in resistance. And instead of having a long straight wire, they decided, well, they could take and coil a wire back and forth a number of times, and you have an effective length, but you have a much smaller area on which that sensor is located. Now, this strain gauge, however, just measures strain in the axis of the gauge. The change in resistance is correlated. Some tests are done. You get something called a gauge factor. If you take courses beyond mechanics materials, you'll probably talk in more detail about strain gauges. You may even apply some strain gauges on your own. So what is done is this strain gauge is glued to a component, and as the material underneath the strain gauge stretches out, the wires of the strain gauge themselves stretch out, and you get this change in resistance. There's a whole lot of effort that goes into applying these strain gauges. You have to use the right kind of glue to transmit the loads and the deformation into the strain gauge. All those things have to be taken into account. You have to use some fairly sensitive instruments in order to measure the strain. Now that said, you probably use strain gauges every day of your life and you don't even realize it. If you've ever gone on a digital bathroom scale, chances are that has a strain gauged beam in it. You hit the toe kick down at the bottom. You are zeroing out the initial strain reading. You stand on the beam on the scale. The beam bends, and it's correlated to weight in either pounds or kilograms, and then that weight gets displayed on the digital display. If you've ever used a digital torque wrench, those are usually strain gauge based. Digital scales of all sorts use strain gauges. Another interesting application of strain gauges is on not only truck stop scales and maybe grocery store scales, but if you've ever seen one of these laptops that have a little post sticking up for a mouse, and it's a mouse button, and you push it forward and the mouse cursor moves one way and you pull it back, well, that is a strain gauged sensor as well, and it can detect which way you're bending that little post. Same idea is used in modern aircraft for the flight stick. You bend it one way or the other, and it senses which way the pilot is trying to maneuver the aircraft, and it applies certain signals accordingly. Let me show you a picture of a strain gauge, and I'll put that up here in just a second. Okay, so here's an image of a strain gauge, and this one is oriented vertically. You can see the loops of wire that go back and forth. And really these days it's not wire anymore, it's a very thin foil. And these big things down here, these are solder terminals. So you take and you solder wires to these solder terminals, and that goes to your instrumentation that can detect the small change in resistance. If you've taken a class in circuits, you might have heard the term Wheatstonebridge. Well, Wheatstonebridge is often used in measuring these very small changes in resistance. So you see it's looping back and forth. And again, this axis of the strain gauge in this case goes vertical, so that means it measures the strain in the vertical direction. Alright, well, let's talk a little bit about strain gauge rosettes, which is a pattern of strain gauges, and it will allow us to measure an entire state of surface strain on a component. Alright, so we talked about strain gauges, and now we're going to talk about strain gauge rosettes. We know that strain gauges measure strain off in the axis of the strain gauge. And I have 3 strain gauges in this picture. I'm just representing those by those kind of patches of those lines. And we're going to make use of our strain gauge, we're going to make use of our strain transformation equation that we just came up with. We're going to write it in this form. Epsilon x prime is equal to epsilon x cosine squared theta plus epsilon y sine squared theta plus gamma xy sine theta cosine theta. And for right now, suppose that we just already know the strains epsilon x, epsilon y, and gamma xy around the area of these strain gauges. We have 3 strain gauges, A, B, and C, and they're located at 3 different angles off the x-axis. If we know the original x and y coordinate strains, then I can come over here and I can write down that the A gauge reading should be equal to epsilon x cosine squared theta A plus epsilon y sine squared theta B, theta A, still, ahead of myself, plus gamma xy sine theta A cosine theta A. So that's what it should read if I know these strains to begin with. And in the same way, I should be able to figure out what the other 2 strain gauges ought to read. It's just the same equation. Instead of having theta A in them, now I'm going to use theta B for the B gauge reading and theta C for the C gauge reading. Now let's think of this the other way around. Suppose I don't know what those strains are, epsilon x, epsilon y, and gamma xy. But I can put these strain gauges on my component and I can measure the strain gauge readings. If we measure this left-hand side, and if we know the angles, then we can solve these equations for the three unknowns. That's how we can get a full state of surface strain. Now there is a catch about these orientations of these strain gauges. You cannot have a pair of these strain gauges being collinear. So that means these angles, you couldn't have one be 180 degrees apart from the other. A pattern of strain gauges is known as a strain gauge rosette. Now those are the general strain gauge rosette equations. However, there are some particular sets of theta A, theta B, and theta C that make life a little easier for us. One type of strain gauge rosette is known as a 0, 45, 90 degree strain gauge rosette. Let's talk about it. Show you a picture in a minute, but for now we're just going to use a sketch. Suppose we have an x and a y-axis, and we decided to put one strain gauge along the x-axis, another along the y-axis, and another strain gauge 45 degrees in between. So this would be the A, the B, and the C gauge. Well, in this case, theta A would be 0 degrees, theta B would be equal to 45, and theta C would be equal to 90 degrees. If I go up to these equations, and I put in 0 degrees, the sine of 0 is 0. So the strain in the x direction would be the reading of the A gauge. And that makes sense because the A gauge is in the x direction. If I go to the C equation and I put in 90 degrees, well, everything drops out except for the epsilon C gauge reading, and the strain in the y direction is the gauge reading epsilon C. If I put in 45 degrees into this middle equation right here, let's go ahead and write it out. Epsilon B would be equal to epsilon x, let's see, 45 degrees, the cosine squared of 45 degrees is 1/2, plus epsilon y, the sine squared of 45 degrees is 1/2, plus gamma xy, and these are also 1/2. If I solve for gamma xy, I'm going to multiply everything by 2. I'll have twice the middle gauge reading minus epsilon x and epsilon y, but since I know those are epsilon A and epsilon C, I'm going to have 2 epsilon B minus epsilon A minus epsilon C. And these three equations are the 0, 45, 90 degree strain gauge rosette equations. We'll use a couple of these for our homework. You'll see 0, 45, 90 degree rosettes in the lab. It's pretty straightforward to use. Strain gauges are probably the most common technique for measuring surface strain in a component that you'll see. It's used a lot. We use a lot of strain gauges at the General Motors Proving Grounds when I worked there. There would be people that would do nothing but instrument parts of cars all day long with these different strain gauges. Let me show you a couple of applications of strain gauges and a picture of a strain gauge rosette. Okay, so this is a picture of a strain gauge rosette, and this one has not been put down on a component yet, just a picture of the gauge itself. you notice the three strain gauges that make up this rosette. Now, the way this is oriented, you're going to have to look at this. Here's the coordinate system. So this would be like the x-axis going this way. This would be the y-axis this way, and this would be the 45-degree bisecting gauge. Now, strain gauges can only sense kind of an average of the strains underneath their gauge pattern. So the assumption here is that the strains don't change very much around this box that I'm going to draw around this strain gauge rosette. And so this would give me my Y strain. This gauge would give me my X strain. And then the 45-degree gauge will help me figure out my shearing strain gamma XY. Now, in some cases, the strains change very quickly over a small area, so you would have to use very small strain gauges. I put on some extremely small strain gauges myself. They're kind of hard to see, they're kind of hard to solder. If your strains don't change very much, then you can get by with a very large strain gauge that's a lot easier to work with. Let me show a picture of some strain gauges. One of my students and I put on a specimen. And there's a weld right in the middle. It's called a plug weld. And we wanted to find out what was going on around the plug weld. These are stacked rosettes, so these three strain gauges lie on top of each other, and they're measuring the strains just like the Rosette equations. And you see the solder terminals. Now these would go off to the instrumentation as different pair of wires to measure that resistance. And down along the bottom are a set of linear strain gauges that helps us determine that we have a uniform strain distribution before we get into this weld zone that's around here. It's hard to see, but there's a kind of a big circular weld right in here. Like I said, strain gauges are probably the most commonly used way to measure strain. The advantage is they're relatively cheap. They're maybe $5 to $10 a piece. It takes some labor and some time to put them on, which isn't necessarily inexpensive. And they are single-use items. Once you glue it on, you can't unglue it and stick it somewhere else. That's it. So there's a lot of surface preparation that has to go into making sure the gauges stick and behave appropriately in order to take good measurements. There are some other techniques to measure strain called full field strain measurements that include some optical methods. You can spray a coating on a component, and you can see what how the thickness of the coating and the optical properties of the coating change when the material underneath of it is stretched out. Those are called full field strain techniques. Those are a little bit beyond what we're going to talk about in this class, but you may take a class, one that I teach is experimental stress analysis, where we get into these different types of strain measurement techniques. Right, we have a little bit more that we want to talk about before we're done with this lecture. So the last thing we want to finish up is we said that we had an equation for gamma x prime y prime that we needed to get, and this idea of a bisecting strain gauge, a 45-degree strain gauge, is going to help us figure that out. Okay, now to see how we can get this gamma x prime y prime equation, we're going to take a look at our coordinate system, our x and y coordinate system, and another coordinate system that's rotated by an angle of theta. So we have their x prime and a y prime directions defined that way. So this would also be the angle theta. And we're going to look at a direction that's 45 degrees in between the x prime and a y prime direction. I'm going to call that the strain epsilon b prime. Now we know that we can write gamma x prime y prime kind of like our 0, 45, 90 degree Rosette equation as twice the middle gauge minus the other two. And I'm going to group them together like this: x prime plus y prime. Now we know about the strain transformation equations for epsilon x and epsilon y, and epsilon x prime and epsilon y prime. Epsilon x prime plus epsilon y prime is equal to epsilon x plus epsilon y. We saw that on the previous page. So I'm going to rewrite this as 2 epsilon b prime minus epsilon x plus epsilon y. If I want to find out what epsilon b prime is in terms of the strains in the x and the y direction, I would use my strain transformation equation for the normal strains. So epsilon b prime would be equal to epsilon x plus epsilon y over 2 plus epsilon x minus epsilon y over 2 cosine. Now, we're not going to theta, but we're going to theta plus 45 degrees. So let's see, instead of theta, what I need right here is 2 theta plus 90 degrees. And then I have my shearing strain gamma xy over 2 sine of 2 theta plus 90 degrees. Alright, so let's go back to my epsilon x prime y prime equation. I know it's 2 times this epsilon b prime, so I'm going to multiply all these terms by 2. And so I have epsilon x plus epsilon y. I'm going to have plus epsilon x minus epsilon y, that quantity. Here I have the cosine of 2 theta plus 90 degrees. That is the negative of the sine of 2 theta. This last term I have, since it's multiplied by 2, gamma xy, and I have the sine of 2 theta plus 90 degrees, and when I shift that by 90 degrees, I end up with a cosine of 2 theta function. And then I have this last term, which is minus epsilon x plus epsilon y. Right, so obviously the first and the last terms now cancel out. And if I divide both sides by 2, I get gamma x prime y prime over 2 is equal to the negative, it's the negative sign from right here, the quantity epsilon x minus epsilon y divided by 2 times the sine of 2 theta plus gamma xy over 2 cosine 2 theta. Alright, so that's the equation that we wanted to show, just to kind of complete that. It helps after, I think it helps to talk about strain gauge rosettes first and then show this equation. Alright, the next lecture will be on the application of strain gauge rosette equations and something called Moore's circle of strain.